People think they understand gravity, but that feeling comes from repetition, not from knowledge. You grow up dropping things, cups, stones, books. They fall every time. After enough years, your mind stops asking questions. Gravity becomes background noise. It feels as obvious as the floor. That confidence is the problem. Because the moment you try to say what gravity does, in a way that lets you predict something new, the easy words stop working. So let's do only what works. Let's describe what happens, carefully, one step at a time, and refuse to guess ahead. Take an object, any object, hold it still, then let go. It begins to move. Not instantly fast. It starts slow, then faster, then faster. That change in motion happens smoothly. Now repeat the experiment with a different object, different size, different material, different weight in your hand. Let go again. The motion changes in exactly the same way. Not almost, not approximately, the same. Now wait, that already contradicts something most people believe. If you ask someone before the experiment, they expect the heavier thing to fall faster. They do not say it out loud anymore, but their body believes it. Their muscles believe it. Their language still carries it, but the experiment refuses. So we write down what we actually see. Every object, when released near Earth, changes its motion in the same way. That statement is precise. It is not a story. It is not an explanation. It is a fact. Now remove the distractions. Air gets in the way. Feathers flutter. Paper drifts. That has nothing to do with gravity. That is the air pushing back. So we remove the air. Drop objects in a vacuum. Now everything behaves the same way again. So gravity does not depend on shape. It does not depend on material. It does not depend on how heavy the object feels. Whatever gravity is doing, it produces the same change in motion for all objects. Now stop and notice how strange that is, because every other influence we know fails this test. Push two objects with the same shove. The lighter one responds more. Heat two objects with the same flame. They warm differently. Charge two objects. They behave differently depending on what they are. Gravity does not care. That is not a metaphor. That is an experimental distinction. Now, people usually say gravity pulls things down. That sounds fine until you ask a technical question. Pulls toward where? If gravity pulled down, then down would mean the same direction everywhere, but it does not. People on opposite sides of Earth both fall toward the ground beneath them. Their down directions point toward each other. So gravity is not down, it is inward. Toward what? Toward Earth's mass. That sounds better, but it is still sloppy, because if mass causes gravity, then more mass should mean a stronger effect on falling speed. But falling speed does not change. So we must separate two ideas that are easy to confuse. First, how strongly gravity acts on an object. Second, how strongly the object resists changes in motion. These are different roles. They do not have to match. But experimentally, they match exactly. Every test ever done shows that the factor that controls how strongly gravity acts is the same factor that controls resistance to motion change. Because they match, they cancel. That cancellation is why all objects fall the same way. We do not explain this cancellation. We use it. Now let's move away from falling objects and make the situation worse. Look at the moon. The moon does not fall straight down. It keeps circling. At first glance, that seems like a different problem. But try this procedure. Imagine the moon with no sideways motion at all. None. Just release it. It falls straight toward Earth. Now give it a little sideways motion. It still falls inward, but now it misses Earth. Give it more sideways motion. It keeps missing. There is no moment where gravity turns off. There is no balance point. The moon is falling the entire time. An orbit is not a suspension. It is continuous falling combined with sideways motion. That is not an interpretation. You can calculate it. You can reproduce it with any object given enough sideways speed. Now pause again. The same rule explains the falling cup and the circling moon without modification. That is already a success. But now comes the next question that ruins comfort. If gravity produces the same change in motion for all objects, why does distance matter? The moon does not fall as fast as the cup, so gravity weakens with distance. How? You measure it. You track motion. You infer how fast motion changes at different distances. You find that the effect decreases in a very specific way as distance increases, not because we prefer that way, because measurements force it. Now here is the key restraint. We do not say gravity knows distance. We do not say gravity reaches out. We do not say gravity spreads. Those words suggest mechanisms we do not observe. All we say is this. Given a mass arrangement, there is a rule that tells you how motion changes at each place. That rule works. It predicts falling objects, it predicts orbits, it predicts tides, it predicts the timing of motion. That is gravity at this level. No story added. Now one more reversal before stopping. When you stand still on the ground, you feel weight. When you fall freely, you feel nothing. That sounds backward until you check what is happening. Standing still requires the ground to continually change your motion. Falling does not. So gravity is not what you feel when you fall. You feel gravity when something prevents you from falling. That statement is not abstract. It is operational. You can test it. Stand on a scale. It reads weight. Remove the support. The reading vanishes. Nothing about gravity changed. Only the constraint did. So gravity describes natural motion when no other influence interferes. Now we pick up exactly where the trouble starts. We already know gravity gives the same change in motion to every object at the same place. That part is settled by experiment. We do not argue it anymore. But the effect is not the same everywhere. So now we ask a narrower question. If gravity changes motion, how does that change depend on where you are, not why? How? So we do not imagine, we measure. You track objects that fall from different heights. You time them. You compare. You do the same thing with objects that move sideways, like projectiles. You do it again with the moon, and again with planets. Every time you extract the same quantity, how fast motion changes at a given distance from Earth. You make a table. Distance from Earth, change in motion. Distance larger, change smaller. Now wait, this is important. The decrease is not arbitrary. It is not linear. It is not random. It follows a strict rule. If you double the distance from Earth's center, the effect becomes 4 times weaker. If you triple the distance, it becomes 9 times weaker. That rule shows up everywhere gravity is measured. Now, we do not say why that rule exists yet. We only accept that it is there because it predicts motion correctly. This is where people usually jump too fast and say inverse square law, as if the name explains it. The name explains nothing. It just labels the behavior. So let's build it instead. Imagine you surround Earth with an imaginary shell at some distance. On that shell, you measure how much gravity affects motion. Now imagine a larger shell, farther out. The same Earth is responsible for both effects. Nothing new is added. But the larger shell has more area. So whatever influence is associated with Earth is now spread across a larger region. The same total effect distributed more thinly. That procedure leads exactly to the distance rule we measure. This is not a metaphor. It is a counting argument. If you accept space as three-dimensional, this rule follows. And here is the restraint. We do not say gravity spreads. We do not say gravity flows. We say only this: the numerical rule that fits all measurements behaves this way with distance. Now we test it. We use it to predict the moon's motion. We calculate how much the moon's motion should change if the same rule applies far away. It matches. We use the same rule for planets. It matches again. No adjustment, no extra terms. So now gravity does two things at once. It gives the same change in motion to all objects at the same place, and it changes with distance in a precise, predictable way. That already puts gravity in a special category. But now we push further. If Earth causes gravity, then smaller masses should cause weaker effects. So we ask, can we detect gravity from something other than Earth? This is not easy. The effect is weak, but it can be done. You take large masses. You suspend small test objects nearby. You isolate everything from vibration. You remove air motion. You wait. The test objects move. Not much, but measurably. They accelerate toward the large masses. So gravity is not exclusive to Earth. Every mass contributes. Again, not a story, an observation. Now we combine facts. Every mass affects motion. The effect weakens with distance. The effect treats all test objects the same. From this, we can write a rule that predicts the change in motion given a distribution of mass. This rule does not tell us what gravity is. It tells us what happens. And now comes a subtle but important point. If every mass affects motion, then every object both falls and causes falling. The cup falls toward Earth. Earth falls toward the cup. You do not notice the second part because Earth is hard to move, but it happens. So gravity is mutual. That is not a philosophical statement. It is required for momentum to be conserved. If Earth did not respond at all, motion accounting would fail. Now test that idea. In a system with two similar masses, both move toward each other. In a system with a small mass and a large one, both move, but the smaller one moves more. The same rule predicts both. So gravity does not single out one object as active and the other as passive. Now notice what we still have not said. We have not said gravity pushes. We have not said gravity pulls. We have not said gravity travels. We only describe changes in motion that can be calculated. Now here is where intuition really starts to fail. If gravity depends on distance, and distance depends on motion, then motion affects gravity's effect. That means gravity and motion are linked in a way that force laws usually are not. So let's do a clean experiment. You throw an object sideways. Gravity changes its vertical motion, but not its sideways motion. At least that is what basic measurement says. But now increase the sideways speed. Make it very large. The path curves differently. Eventually, the object no longer hits the ground. It circles. Gravity has not changed. The object's motion has. So gravity does not dictate a path. It dictates how motion changes. That distinction matters. Because once you frame gravity as a rule for how motion changes rather than a push, a lot of confusion disappears. We are not saying what gravity does to objects. We are saying how objects move when gravity is the only influence. That is an operational statement. You can remove all other influences and test it. Now we stop here deliberately, because the next step requires changing how we think about straight motion itself. And if we rush into that too soon, it sounds like wordplay. So we stop with this inventory. Gravity gives the same change in motion to all objects at the same place. It weakens with distance in a precise way. Every mass contributes. Motion under gravity is predictable without knowing what gravity is. That is all we have earned so far. Now we reach the point where the usual force picture starts to crack. Up to now, we have treated gravity as a rule that tells you how motion changes when nothing else interferes. That works for falling objects. It works for orbits. It works for anything you can drop, throw, or track. But there is a deeper test. We ask whether gravity can be removed, not reduced, not weakened, removed. So we try the cleanest possible experiment. You build a closed box, thick walls, no windows, nothing to look out of. Inside the box you place an object. You release it. It falls. Now you do something else. You put the same box far from Earth. No nearby masses. No measurable gravity at all. You attach a rocket to the box. You fire the rocket so the box accelerates. You release the object again. It falls. Now wait. Falls relative to what? Relative to the box. In both cases, the object moves the same way with respect to the walls of the box. You measure times. You measure distances. You compare motions. You cannot tell which situation you are in. That is not a thought game. It is a rule you can test. If gravity acted differently from acceleration, the motions would differ. They do not. So we arrive at a statement that is almost uncomfortable. Being in a gravitational field and being in an accelerating system produce the same local effects. Not approximately, exactly, as far as experiments can tell. This is not a belief. It is forced by observation. Now slow down. This is delicate. We are not saying gravity is acceleration. We are saying that locally, meaning in a small enough region, there is no experiment that can tell them apart. So any explanation of gravity that depends on a special gravitational push immediately runs into trouble. because acceleration without gravity produces the same effects. Now test this idea again. Inside the accelerating box, objects fall. Liquids form surfaces. Light travels in straight lines relative to the box. No, wait. That is where it gets interesting. You send a beam of light across the box, sideways. While the light travels, the box accelerates upward. So by the time the light reaches the other wall, the wall has moved. The light hits lower than where it started. So inside the accelerating box, light appears to bend. Now return to the first situation, the box sitting on Earth. If the two situations are indistinguishable, then light must also bend in a gravitational field. That is not optional, that is forced. So now we have a prediction. Light, even though it has no mass in the usual sense, must have its motion affected by gravity. We can test this. We look at light from distant stars as it passes near a massive body. We measure where it appears. It is displaced. The amount matches the prediction. Now pause again. We did not assume gravity pulls on light. We did not add a new rule. We took one experimentally unavoidable statement. Acceleration and gravity are locally indistinguishable, and followed it to a consequence. That consequence is correct. Now look at what just happened to the force picture. A force usually acts on something that resists it. Light does not resist changes in motion the way objects with mass do, yet its path is affected. So gravity cannot be acting like an ordinary force. It cannot be pushing. It cannot be tugging. It is doing something else. But before saying what that something else is, we do another experiment. Inside the falling box, not the accelerating one, the freely falling one, you release objects. They float. They do not fall toward the floor. They stay where they are. Now, wait, that means something important. Inside a freely falling system, gravity disappears. Not approximately, exactly. That is not poetry, that is operational. You can test it. Drop the box, release objects, measure their motion relative to the box. They do not accelerate. So gravity is present when objects are prevented from following their natural motion. Gravity is absent when objects are allowed to follow it. This is the same reversal we noticed earlier with weight. Now we push it further. If gravity vanishes in free fall, then gravity is not something added to motion. It is something that shows up when motion is constrained. That is a dangerous sentence, so let me clean it. We are not saying gravity turns off. We are saying the effects attributed to gravity can be removed by choosing a freely falling frame. That is an experimental fact. Now we ask the next hard question. If gravity can be removed locally by changing motion, then gravity is not a property of objects. It is a property of how motion is described. That sounds abstract, so let's anchor it. Straight motion is defined as motion that requires no intervention. Inside the falling box, objects move straight. Outside the box, standing on the ground, the same motion looks curved. So what counts as straight depends on the situation, and that dependence is controlled by mass distribution. Now notice how carefully we are moving. We have not said anything about space being bent. We have not drawn pictures. We have only said this: the rule that tells you which motions require no intervention depends on where mass is. That is a rule you can use. Given mass arrangement, you can calculate which paths count as natural. And once you know that, everything else follows. Objects follow those paths. Light follows those paths. Clocks follow those paths. Now we stop again, because from here on, the language becomes dangerous if used too early. So we inventory what is now forced on us. Gravity is indistinguishable from acceleration in small regions. Light's motion is affected by gravity. Gravity can be removed locally by free fall. What counts as straight motion depends on mass. None of that is interpretation. All of it is experimental or logical consequence. Now we have to be extremely careful, because this is the place where people usually stop doing physics and start telling stories. So we will not tell stories, we will build rules. Up to now, everything we have said can be checked with falling boxes, clocks, light beams, and motion measurements. No pictures were required, just procedures. Now we ask the next necessary question. If gravity can be removed locally by free fall, but not globally, then what remains? Something must still distinguish one place from another. Otherwise, nothing would ever curve, and the moon would not orbit. So the effect of gravity is not gone. It is just hidden locally. So where does it show up? It shows up when you compare motion in different places. That comparison is unavoidable. Here is the experiment. You take two objects. You place them some distance apart. You release both in free fall. Locally, near each object, everything looks ordinary. No gravity, no acceleration. But now you compare their motion. Do they remain the same distance apart? Sometimes yes, sometimes no. Near Earth, two objects dropped side by side slowly move closer together as they fall. That is measurable. They are both falling freely, and yet their separation changes. So gravity has not vanished. It has changed form. Instead of showing up as a force on each object, it shows up as a change in how nearby motions compare. That is not interpretation, that is observation. So now we have to describe gravity in a new way, not as a force acting on objects, but as a rule governing how families of nearby motions evolve relative to one another. This is already enough to abandon the force picture. Because forces act on single objects, what we are now seeing is an effect that shows up only when you compare multiple objects. So gravity is about relationships between motions. Now we tighten it. If you want to describe motion without gravity, you say, objects move in straight lines unless acted on. That definition of straight is operational. You check whether motion requires intervention. Now, in the presence of gravity, that definition breaks. An object that is falling freely requires no intervention, yet its path looks curved when compared to distant reference points. So either the object is not moving straight, or our definition of straight is incomplete. The experiments force the second option. So we refine the rule. Straight motion means motion that requires no local intervention. That is all. Once you adopt that definition, falling objects move straight. Light moves straight. Anything not constrained moves straight. So where does curvature come from? From comparison across space. You compare two locally straight motions in different places, and they do not align. That mismatch is gravity. Now pause. Notice what we have done without saying it out loud. We have moved gravity out of objects and into the structure that compares motion across space and time. But we are still not allowed to say anything vague, so we give ourselves a task. Given a distribution of mass, we want a rule that tells us how locally straight motions compare across space. That rule must predict falling objects, orbits, light, bending, clock, rates, tidal effects, and it must reduce to ordinary motion when gravity is absent. That is a tall order, but it can be done. Now here is the key constraint. The rule cannot depend on what object you use to probe it, because all objects fall the same way. So the rule must depend only on position and motion, not on mass or composition. That immediately rules out many possible descriptions. Now we search for something that satisfies all constraints. We need a mathematical structure that tells you what straight motion means locally, lets straightness vary from place to place, depends only on mass distribution, applies equally to all objects and light. There is only one known structure that does this cleanly. It is a rule that assigns relationships between nearby positions and times. Once those relationships are specified, straight motion is determined. No force is required, no extra assumptions. Now I will say the dangerous sentence, but only after earning it. Gravity is not something that happens in space and time. It is something that determines how space and time relate motion. That sentence sounds abstract, so let me translate it back into procedure. Given mass distribution, you compute certain relationships between nearby positions and times. From those relationships, you calculate which motions require no intervention. Those motions are what objects follow when left alone. That is gravity. Now test it. You compute those relationships near Earth. You calculate natural paths. They curve inward. You compute them far away. They straighten. You compute them near massive bodies. Light paths curve. You compute clock behavior. Clocks run at different rates in different places. Those are not added effects. They fall out of the same rule. Now pause again. Notice how little we assumed. We did not assume gravity pulls. We did not assume gravity propagates. We did not assume gravity prefers mass. We assumed only what experiments forced: local equivalence of gravity and acceleration, universality of free fall, predictability of motion. Everything else follows. Now here is the last important check before we move on. If this description is correct, then energy and motion accounting must still work. Objects must exchange motion consistently. No energy should appear or vanish. That is not automatic, but when the calculations are done carefully, accounting works. Momentum is conserved. Energy is conserved in the proper sense. So the new description does not break older successes. It contains them. Now we stop again, because the final step is to confront what this description does not tell us, and that matters just as much. Up to now, we have built gravity only from things we are forced to accept. We did not guess what gravity is made of. We did not invent pictures. We did not add causes that cannot be tested. We asked only this: given how motion behaves, what rule predicts it? And we found such a rule. It tells us how to calculate motion when mass is present. It tells us how clocks behave. It tells us how light travels. It tells us how objects fall, orbit, and separate. It does all of that correctly. Now we ask the final question: does this rule explain gravity? The answer is no. And that is not a failure. That is a fact. Because explanation in the usual sense means reducing one thing to something more familiar. And nothing underneath this rule is more familiar. You can ask what causes gravity, but the question stops being productive, because gravity is not sitting on top of something simpler. It is already at the bottom of the ladder, as far as we can tell. Now let's be precise about what we mean. We have a rule that takes mass distribution as input and gives motion as output. We do not know why that rule is the rule. We do not know why mass affects motion this way and not another way. We do not know why the cancellation between gravitational action and resistance to motion is exact. We do not know why light follows the same natural paths as objects. Those are not missing pieces of calculation. They are missing pieces of explanation, and physics is honest about that. Now, check something important. Despite not knowing why the rule is what it is, we can use it. We can predict motion with extreme accuracy. We can send objects around Earth and bring them back. We can predict clock differences. We can correct navigation systems. We can predict gravitational waves and detect them. All of that works. So gravity as a theory is complete in one sense and incomplete in another. Complete for prediction, incomplete for explanation. Now notice something subtle. People often feel uneasy about this and try to repair it by adding stories. They say space is curved like a surface. They say mass tells space how to bend. They draw diagrams. Those pictures are not wrong, but they are not the theory. They are translation aids. If you take them too seriously, they mislead you, because space is not a rubber sheet, and mass does not push on it. The actual theory is a calculation procedure. Given mass distribution, compute certain quantities. From those quantities, compute motion. That is all. Now, one last experimental check. If gravity were an ordinary force, then it should combine with other forces in the same way. But it does not. Gravity affects everything, even energy stored in motion itself. Light bends. Time behaves differently. That already tells you gravity does not sit alongside other forces. It reorganizes the stage on which they act. But, and this is important, that does not mean gravity explains the others. It coexists with them. And here is the remaining problem. When we try to combine gravity with the rules that govern very small systems, things stop working cleanly. Calculations blow up. Predictions fail. Not because gravity is vague, but because our methods clash. So gravity stands in an odd position. It is extremely precise. It is extremely reliable. And it refuses to fit neatly with everything else. That is not something to fix with words. It is something to fix with better rules or to accept as a boundary. Now let me end by undoing one last misunderstanding. People think gravity is mysterious because it is hard to imagine. That is not the problem. Electricity is hard to imagine too. The difference is this. For electricity, we can imagine causes beneath the rule. For gravity, every attempt to do that collapses back into the same rule. So the correct attitude is not comfort, it is discipline. We do not pretend to know more than we do. We do not replace rules with pictures. We use the rule. We test the rule. We respect where it stops answering questions. That is not giving up. That is how physics stays honest. And that is gravity, as far as we can take it without lying.